Hello world and welcome back to Money Makes Games. Today we're going to talk about hoverboards. I don't know about you, but ever since I was a little boy, each time I'd watch Back to the Future, I'd think, whoa, I'd really like one of those. So when Greg from Midnight Oil Software asked me to help him out with the problem on his hoverboard, I thought, oh, that would be cool. Little did I know how quickly you could get stuck when playing with a hoverboard. So, let's find out what the issues were and how we fix them. My name is Moni, and I make games. Let's start off by thinking about what a hoverboard is and what it's supposed to do. The word implies that a hoverboard would be like a cross between a hovercraft and a skateboard. So that would mean something that floats on a cushion of air or maybe is levitated by some as yet undiscovered anti-gravity force. So how would we implement this? Well, mostly you would take a board or a rigid body with a script attached that basically detects when gravity is pulling it down to a certain height, and if you fall below that height, you would apply an upward force to counter gravity and so stay up in the air. Pretty easy so far. Then you would probably add something like a script to apply a force at the back to move forward, or maybe even a force at the front to move backwards, and a torque force to turn your board. This is where we're at the moment, and I'll show you the script for this in a while. But let's have a look and see what's going on here. I want you to notice something right there. If you look at our board, notice that our board's collider is actually hitting the hill, which means that you're going to get stuck at some point or have a collision where the board is, severely jolting, slowing down, going off course. The other thing to notice is this angle here. We would expect a hoverboard to behave more like something that's riding on a cushion of air. In other words, conforming to the terrain. So if you're going uphill, you would expect the angle of our hoverboard to be something like this. So how do we handle this? Well, let's see where we started off, and then I'll show you what we came up with. So this is our basic hoverboard. As you can see, we've got our 3D mesh with a box collider attached to it and a rigid body that uses gravity and is dynamic. Now, look down here. Do you see this freeze rotation? We need to do this to assure that the hoverboard doesn't actually fall over when it gets slightly unstable or makes a collision. To demonstrate my point, let's run. Oh, didn't even get off the ground that time. And we're stuck. That's one of the problems we have, because if we want our hoverboard to conform to the terrain angle, we don't want that. Okay, to understand why this is happening, let's go look at the rest of our setup and our current code. So what we have here is we have our hover height that's set. Then we have a hover force that we apply, and we have a dampening value. The rest is Pretty easy. That's just our transform, our rigid body, and an array for raycast hits. So we initialize everything here, and then in fixed update, which is where you want to always do your physics stuff, we do a raycast from our current transform.position in the direction of the down for our transform. We store that in hits, and we make the raycast as long as our target hover height. Okay, so if we did get a hit on the ground, we would take the hover height and subtract the distance from our current transform dot position to the actual point that we hit the ground with our cast. And then we would calculate a force vector for that by taking force.up, in other words, the general up direction, and multiplying that by the amount we get when we take this difference in height and multiply it by the hover force. Then, of course, we just take our rigid body, add that upward force, and now our hoverboard is floating. Now all that's left is to dampen the velocity of our rigid body so that it doesn't keep bouncing and never actually settles down into position. To do this, we create a vector 3 to store our current velocity. We take the rigid body's velocity and we assign that. And then we take 1 and we subtract the damping force times time.delta time. Time.fixed delta time, because we are working in fixed delta time, to make sure that this is frame rate independent. And then we take that number, which is now smaller than 1 and represents a fraction of our velocity, and we times the velocity with that number to get the smaller velocity, and we reassign that back to our rigid body. As far as the move player script goes, again, initialize so we can get our rigid body and our transform. We handle input by basically just getting the axes from the input system. And then we handle the movement by applying a torque for our turns, or by applying a force to our rigid body in the transform.forward direction. That would be positive for forward if we have a positive vertical input, and negative for backwards. How do we fix the problems with this system? Well, let's identify them first. Number 1, we need to figure out how to conform to the terrain. Number 2, we need to find a way to predict what the terrain is, to start rotating beforehand to avoid actually hitting the terrain with the front of our collider, or with the side if we're sliding, or with the back. Now that we know which problems we want to solve, I'll show you what I came up with, and you can see what works, what doesn't, and where we can improve. And we're back. So let's look at what changed. Notice when we crest our hills that we are no longer getting stuck on a hill, and that the hoverboard is actually conforming to the landscape. It matches the angle of the ground, but also if you look at the right hand scene, you'll see a red dot moving in front of the board, approximately in the direction that the velocity of the board is going. This is the new raycast point that we're using to determine the height off the ground, which I'll explain in a moment. The important thing to realize here is that this point will get to a hill or a height or a dip before the board gets here, which means you can start adjusting your height as you are approaching. Okay, there's another thing that we've added here, and that's the ability to change the roll and the pitch of the board. Right, let's have a look at our code and see how this happened. Looking at our code, you'll see that it's grown quite a bit. I'm not going to go into every variable that I've added, but you can check out the code on the GitLab repository that I've linked in the description. Let's look at our fixed update. We've still got our variable to store how many raycast hits we have, but now we have a vector 3 here called raycast advanced. This is going to be used to determine the new raycast position to set the height for our hoverboard. We figure out where we want this to be by firstly going rigid body transform.up, which gives us the up direction of our rigid body, and we multiply that by a variable called raycast height above board, which is used to determine how high up we want to do our raycast. And then we also take the rigid body's velocity, which is a vector 3 as well, and multiplying that by the factor of the velocity look ahead, which we've also defined. And this will give us a point that is above the board by a set height and traveling ahead of the board in whichever direction our board is traveling. Why do we do it this way? Well, firstly, we want to be slightly above the board, because if our board does bottom out on a crest or due to a hard fall, we don't want our cast point to fall below the terrain, which means we'll be getting 0 hits and we'll also be getting 0 force to lift the board up again. Secondly, we want our raycast point to travel ahead of the board so that if there's a terrain change up ahead, we can already start calculating the new height needed and start moving the board in that direction. Now that we've got our advance and we know where we'll be casting from, we set about the business of doing our raycast, which has also changed slightly because now we need to take into account the new raycast position by adding it to our transform.position. And we'll also be taking the target hover height and actually adding the height of our raycast position above the ground. Otherwise, let's say we've set our position to 2 units above the board and our target hover height is only 0.8 units. Then we'll be casting a ray down from the cast point with a length of 0.8 units and never actually hitting the ground while our board is lying on the ground doing nothing. Then we check if we had any hits. As usual, we determine the difference in height, once again taking into account the raycast height above the ground. And then we calculate our force as we've done before by taking the transform.up and multiplying the error by the hover force. Error, of course, being the difference in height between where we want to be and where we are. Note here that if we are higher than the target hover height, we won't get any hits on the ground, and therefore our board won't push itself up and it will naturally fall to the ground under the force of gravity. Then we just add our force and move on. Now what's this? Why am I doing the same thing again? If you look at this, we're doing another raycast, but this time from the center position of the board and above by the set amount for our raycast height above board. And here we once again adjust the length of our ray by using that raycast height above board. But why do this? The reason for this is actually very simple. Let's say we are approaching a hill right here. Now when we initially come here, We'll assume that our raycast is going down here. It detects the hill and adjusts the height of our board. All is well. But now what happens when we get here? Our raycast is advanced ahead of the board, cast down, gets a new height, and the board drops down to conform. Now, if this height difference is too much, our board is going to bottom out. So, to avoid that, we do a second cast at the center point of our board, just to check, and if we are too low here, we just give it a little kick to keep it off the ground. And that's it. After that, we move on to our damping code that we had before. And then we get to two new functions that I've added. The first one is set lean angles, and the second one is attitude adjust. The code for set lean angles is pretty basic. All we're doing is checking for keyboard inputs. And what this does is to set the desired angles for our pitch and roll, which we will use in the attitude adjust. And then also down here, I've put in a little bit of code to check if we have keycode.space, which means that if we press space, we add a force to our rigid body and make our board jump. Of course, you'll notice here that there's no ground checking here. Because this is a hoverboard, we might be able to do a little double jump and use that mysterious anti-gravity force to our advantage. So what does attitude adjust actually do? Well, this is where we keep our board upright without freezing our rotation as we've had to do before. So we can take freeze rotation off our rigid body, and we take our current forward and get that from our rigid body by asking it for its transform.forward, and we get the normalized value, which is very important for this to work. Then we create our up vector, which will be setting as vector3.up. Now the reason why we want a forward and an up is because at the end of the day, we'll be using quaternion.look rotation to set the correct rotation for our board. And this needs a forward and an up rotation to set the correct rotation. From here on out, we do a little raycast. From our raycast advanced position, we cast it down, and we take the target hover height plus 4. This needs to be improved to take into consideration the new cast position, but it's working for now, so we're not going to mess with it too much. Now, if we do get hits, we change the up vector to hits.normal. This means we'll be hitting the ground and getting the normal for the terrain. Firstly, why did we set up vector as vector3.up and then try to set it here again? The reasoning is simple. If you go over a high jump or fall off the side of a cliff, you want your board to try to go to the upright position. So we keep it safe by making the default vector3.up. But if we do get the ground normal, we're going to try and orient our board in this direction. Now, for those who don't know what the normal is, a normal is basically a line that runs perpendicular to the ground. So, the easiest way to demonstrate this is to get a normal. If you notice the angle of this white line, it runs perpendicular to the ground. Now in this little simplified simulation, that white line represents the normal for the ground, And the green line we'll talk about in a little bit, as well as the red line. The blue line is our current forward. So let's get back to the code and I'll make things clear. Now what we want to do is get that forward direction that we can feed into the quaternion.look rotation. So to do that, we're going to go forward equals current forward minus, and we can put this in brackets, up vector times the dot product of the current forward and the up vector. You'll also see at the end here I've added transform.up times the lean back amount. This is going to change the pitch of the hoverboard, but it's not important for what we're doing right now. What I want to do is for us to have a quick look at this equation and try to see if we can understand it a little bit better. Let's start this off by looking at a property of the dot product of two vectors that we'll be using. If you take two normalized vectors and you calculate their dot products, you'll see a pattern emerging. Firstly, if your two vectors are exactly the same, the dot product for the two vectors will be 1. That means the two vectors are pointing in the same direction. Now, if you take those two normalized vectors and they are perpendicular, the dot product for them will have a result of 0. And if they are opposing vectors, that means the dot product will be -1. We're using normalized vectors for all these calculations, so the magnitude of the vector makes no difference. It's purely about the direction. Now, in our case, for our hoverboard, this is our ground normal, which is our up vector, and this is our current forward. So we'll call this up, and we'll call this forward. Now, as you can see, the difference here is more than 90 degrees. That means the dot product for this will fall somewhere between 0 and -1. If this vector was actually going this way, in other words, we were going downhill like this, the dot product for the two vectors would have been between 0 and 1, which is a positive value. So let's try to play this equation out and see what happens. We're going to use normalized vectors. This is going to be a vector of size -1 and 1. In other words, it's going up by 1 unit and 1 unit left. And this is going to be a vector of 1 and 0. In other words, a vector going 1 unit to the right and 0 up or down. Now this one's already normalized. We need to normalize this vector, which means that it actually becomes negative 0.7 and 0.7. These are only the approximate values. So let's write out our equation. We have got our vector 1, 0 minus, and let's use brackets here to keep everything straight. We are going to do the up vector, which is minus 0.7, 0.7, and we are going to multiply it by the dot product of these two. Now, what's the dot product of these two? We can calculate that by taking the x of each one and multiplying them together and then adding the y times the y. So if we work this out, 0.7 times 0 is obviously 0. So we have minus 0.7 times 1. And this is our dot product. Now if we take this a little further, we'll stick to that. Go negative there. Now we multiply this negative number in there, which means we get positive 0.49 and negative 0.49. If we play this out, we end up with a vector of 0.51 and 0.49. If you had to draw this vector would be going up by half a unit and to the right by half a unit. So it would look something like that. This isn't drawn accurately. If it was drawn accurately, you would end up with a perpendicular vector to that one, which would be parallel to the ground. So what would have happened if this was a positive number? Well, these two would have changed in that you would have ended up with a positive number here, which you would subtract, and you would end up with a vector going down like this. Now let's use our 2D visualizer to see exactly how this works. So here we have our hoverboard. It's at the start of our hill and it's casting a ray straight down. Let's draw our vectors and see what's going on. Now the white line here represents your ground normal. In other words, this is a line perpendicular to the ground angle where the ray hit. This is our forward direction at the moment. This is going to be the direction we want to rotate towards. And this here is the result of taking the up vector and multiplying it by that dot product we talked about. Now, if you look at this, you'll see that the green line, which represents this dot product, is pointing downwards. That actually means that we have a negative scalar for the dot product, which we've multiplied with the up direction, resulting in a vector that's going in the opposite direction of the ground normal. Now, if we move to this side, now we've got our hit here where the ground angle is actually going this way. You can see that our normal is pointing this way and that the angle between the forward direction and the direction of the normal or our up vector is less than 90 degrees, and that has resulted in a positive value for the dot product. And then also notice that eventually your up vector is perpendicular to the desired vector that we've calculated. So finally, back in our code, we've calculated the forward vector that we need. We take that, we plug it into the forward vector parameter for our quaternion.look rotation. We take our up vector, and to get the roll for our hoverboard right, we add transform.right multiplied by the lean side amount that we specified. Then, to get to this rotation, instead of just snapping to it, we slurp from our current rotation towards the look rotation that we want to calculate. And then we move that at a rate determined by time.fixed delta time to stay frame rate independent, multiplied by a rotation rate that we have specified as a variable. Our last thing I want to show you is just this little piece of code. This is the onDraw gizmos call that Unity issues, like your start and your update calls. And when it gets called, I just said gizmos, set the color of my gizmo to red so I can see it clearly. And then draw a sphere at the position of your transform plus the raycast advance. And then just make that sphere 0.1 units big. And finally, we're back in the editor and our hoverboard is ready to go. A quick note here, you'll notice that my terrain is set to the layer that I called ground. If you don't have a layer, you could just add one, call it ground. And then on the hoverboard, where I have my ground mask field, I've set that to the terrain layer, which I called ground. We use this to filter our raycast so that we don't get unnecessary hits from our board if the cast point passes over the position of the board, or if we have a player later on, or anything else that might interfere with our hover script. I've put the code for this up on GitLab, and I'm now handing this over to you. So go ahead, play with it, make something better, or just learn from it. If you do make something nice, let me know by dropping a comment with a link. If you like what I did, give me a like and a subscribe. And until we see each other, my name is Mani, and I'm saying goodbye.